So finishing 1-1. First thing we start about is coterminal angles. So it's an angle in standard position on a rotation from 0 to 2 pi or 0 to 360 degrees. And you must add or subtract 360 or 2 pi to find the coterminal angle. So basically, we know on our graph that we have 360 degrees for one rotation, correct? Now, if I have something that is, let's go 450 degrees, okay? That's still an angle, but technically, I go the whole way around. This is 360, and then I have to keep going to here, correct? This would be 450 degrees. Now that doesn't really make a whole lot of sense to us. All right? Everything we do is based on that one rotation around. Okay? After that, it just becomes repetitive. So what we're doing is we're going to take an angle that's bigger than 360 or bigger than 2 pi and make it back to a standard angle. So in this case, for instance, I went the whole way around, and then I said it was, what did I say, 450? Oh, yeah, 450. So then, what's 450 minus 360? 90. All right, that gets my 90-degree angle. So therefore, 450 degrees is exactly the same angle as 90 degrees. Okay? Because everything we do is based off of that. All right, so if I'm standing here, all right, if I'm looking, I'll stand in front of the class. So I'm looking straight this direction. If I spin 360, or if I spin 90 degrees, I'm right here. Correct? All right, back to the original. I'm going to spin 450 degrees. All right, 360, 450. Did I end up in the same spot? Yeah, it's the same angle. Does that make sense? All right. So, if we want to find a coterminal angle, we're going to do a couple. First one, 420 degrees. So is that bigger than 360? Yeah, it's a positive number. It's bigger than 360, so just take it and subtract 360 off of it. What am I left with? 60 degrees. Does that fall between 0 and 360? Yes, it does, so we're good. Stop right there. 420 is the same as 60 degrees. That's exactly it. That's an easy one, yep. It's easier in degrees here. Now, you can also do this with negatives. All right, we want something to be a standard angle. It has to go from 0 to 360. Now, if I come back over here to my little picture, negative 120 degrees would be starting, I'm just going to start over. So negative 120 degrees would be starting at the same spot and going this direction. Okay, that would be negative 120. It would be down here. Okay, but again, our standard angle, our things that we work with are going to be from 0 to 360 or 0 to 2 pi on that one rotation. So I'm more interested in this angle. Okay, so this angle up top and this angle right here are going to be exactly the same. Okay, so now I put up here in the parentheses subtract if positive, add if negative, right? This one's negative, so I want to add 360 to it. Add 360 takes me to what? 240? Is that between 0 and 360? Yeah, I'm good. I'm done. Stop right there. All right. Let's look at a couple in radians. If I have 17 pi over 6. All right, that's obviously bigger than 2 pi, right? Okay, because 12 pi over 6 would be 2 pi. Okay, so now when you're in radians, though, you want to subtract 2 pi. What do I need, though? Common denominators, right? So I need a common denominator. So in this case, I'm going to have 17 pi over 6. My common denominator is going to be 6. So I'm going to make this 12 pi over 6, which is going to be what then? 5 pi over 6, correct. Okay. Same aspect if I have a negative radian. Phi of negative pi over 12. I'm going the wrong direction. Now I'm going clockwise around my rotation, and it doesn't work as nicely that way. All right, so if I want to do that, it's a negative, so I add. In this case, I'm going to add 2 pi. Add 2 pi, find a common denominator, so it's negative pi over 12 plus 24 pi over 12. And that's going to give me what then? 23 pi over 12. And then, after you add or subtract, make sure you check it. Okay, make sure you stop and check yourself to make sure it's in that range. 0 to 360, 0 to 2 pi. We do one more here and you'll see what I'm talking about. So phi is 750 degrees. Okay, 750, that's obviously too big. It's bigger than 360. So I subtract off of 360, what do I get? 390. Still bigger than 360, isn't it? So subtract 360 again. Subtract 360 again. Now I got 30 degrees. In this case, the one we just did, it would be 750 degrees would be 1, 2 rotations, and then to about right there. Okay? That would be 750 degrees. Or instead, we can just look at this angle right here. Just makes life so much easier on us.
So is there like a specific way that we would have to write this, like whether we put it down there, or?
That or that. That's the final answer for the coterminal angle. Okay. All right. So let's, first off, any questions on that? Okay. All right. Now, sometimes we're going to find the length of a circular arc. So circular arc is going to, the arc is the distance around the outside, essentially. Okay. You have a circumference, is the distance around the entire part. If we want to find the length of an arc, that's just a segment of it. Okay, so let r be the radius of the circle and theta be the non-negative radian measure of a central angle of the circle. The length of the arc interrupted by the central angle is s equals r times theta. And this only works in radians. All right, so I'm drawing my circle. This would be the intercepted arc. I'm looking at this section right here. Okay, this is my theta. This would be my radius from the center to the edge. And then here would be my arc length. That part that I kind of scribbled on. Okay. All right. So then for an example here, we want to find the arc length for a segment that's 120 degrees of the circle with a radius of 10 inches. Now, the thing above says it only works for radians, right? So what do you want to do with 120 degrees first? Change it to radians. Okay. So 120 degrees, what do we have to multiply by to get something from degrees or radians? Pi over 180, correct. Pi over 180. So then I'm looking at 120 pi over 180, which that's going to simplify 12 over 18, which is going to be 2/3. So I'm looking at 2/3 pi. All right. So then S, which is my arc length, is going to be equal to the radius. The radius is what in this case? It's 10. It's given here, right? Radius is 10. The theta, or is my angle that intersects it. So now I just punch that in the calculator. Wow. I got 20 pi over 3. I could leave it like that. If I say give me an exact answer, that would be an exact answer. Okay. If I wanted an estimate, if I wanted approximated, I could take this to, comes out as 20.94 inches. That's the 2 decimal places. Okay. Now again, I said this only works in radians, right? That formula as written only works in radians. We could do this with degrees. When you do it with degrees, you'd have to put 120 over 360, then multiply it times the circumference. All right. And it just becomes a longer process. So it's just much easier to go ahead, put this in radians, and then roll with it. Make sense? All right. Let's keep rolling. Now, same aspect. We have area of a sector. You guys might remember this from geometry. Okay, the area of a sector of a circle. Sector is a portion of a circle's interior formed by a central angle theta. All right, so looking at the circle here, I might have something like this and this. Okay. I don't like that. It should be straight out the side. All right. So then this is my theta inside here, whatever I'm cutting off. So the area is this section here. Okay, it's that segment there. Your slice of pizza. All right, for lack of a better way to put it. All right, so you're looking for the area of that pizza slice. So to find the area of the sector, here's your formula. Let r be the radius of a circle and theta the non-negative radian measure of a central angle of the circle. Area of the sector formed by the central angle is 1/2 r squared times theta. And again, this formula only works in radians. So we got an example here. I want to find the area of the sector of a circle that has a radius of 4 feet and an intersected angle of 60 degrees. So we need to do what with ours first? Change it to radians. Okay, so 60 degrees multiplied by pi over 180. So I'm going to have 60 pi over 180, which is going to be 1/3, right? Or pi over 3. So then if I want to find the area, just plug in what I have. 1/2 the radius squared. Okay, the radius is 4 squared times pi over 3. All right, so 4 squared is 16 times 1/2 is going to be 8. So I'm looking at 8 pi over 3. That'd be 8 pi over 3 feet squared, which would be roughly 8.38 feet squared. Questions on that? Okay. What? What it comes out to be? I have it written down on my note sheet. But it just, yeah, just punch in the calculator. 8 times pi divided by 3. It's area. It's feet squared.
I was about to say, there's no way you did that in your head.
Well, I mean, there could be a way.
I mean, you'd have to.
Well, I mean, just look at it like this, though. Pi is barely over 3, right?
Yeah.
So you could almost cancel out the 3's. You know it's going to be a little bit over 8.
Yeah.
I could have looked at that real quick and said it was 8 point something low. You know what I mean?
Yeah, that one makes sense. I mean, for
Other ones, yeah. Yeah.
Where like maybe the denominator's like 5.
Yeah. I'm good, but I'm not that good. All right, number 2 is up there. Radius is 11 inches. Angle is 45 degrees. Take a minute and try that one on your own. So, second problem. All right, we changed it from degrees to radians. So what's it going to be in radians? Anybody? Pi over 4, right?
Yes.
Okay. That's the radian degree. Okay, pi over 4. Plug it in. You good there, Submont?
Yeah, I just forgot to write the 20 as a 4.
All right, so we have 1/2 11 squared pi over 4, right? So we're looking at what, 60.5 over 4? Is that what you got? And then what's that come out to be? No one has a calculator?
Just waiting. I tried looking it up, but I don't know.
Have it on your paper.
I don't have a
I don't have that one.
No, I do. Never mind.
Yeah, you do.
47.5? That's what I got.
I'll buy that. 47.5,
5'1".
and this would be inches squared. Okay?
My numbers were all, they were all the same.
We go with that? No problem? All right. So linear and angular speed. I think these ones are fun. All right, so linear and angular speed. If a point is in motion on a circle of radius r through an angle of theta radians in time t, then its linear speed is v equals s over t, where s is the arc length given by s r theta, and its angular speed is w equals theta over t. All right, so there's a lot going on there, right? There's a lot going on, and that's okay. All right, so linear and angular speed. Linear speed is the speed that something is moving in a straight line, essentially. Okay. Angular speed is how fast the angle is changing within the circle. Okay, so if I put my hands together like this, there's an angle, right? So from here to here, however fast that I'm opening, that is angular speed. Okay, so right now that might be 6 inches a second. Like I have no clue. You know what I mean? So if you want to look at it like that, and again, I'm keeping that pivot point. So the speed that this is changing in here that's my angular speed. All right, so we look at the bottom. Hard drive rotates at 3,600 RPM. What's the angular speed of a point on the drive? Okay, so the first thing we got to do is we want to find our I can't read my own writing. Okay, so if we're looking for the angular speed, we just essentially want to use this as like a almost like a conversion rate, for lack of a better way to put it. Okay, so what is our speed right now, though? 3,600 RPM. One rotation is the same as a revolution, right? Okay, it's the same. The word means the same. So that means every minute we're making 3,600 revolutions. Would you agree with me?
Yeah.
Okay. So if that is the speed that it's rotating right now we just need to change it into radians, essentially. If we change it into radians, that's going to be our angular speed, so we're just worried about that angle. All right. So if I look at this right now, I want to make this into radians. So 2 pi radians. Remember back to how our unit rates change. We want to cancel stuff out, right? Well, 2 pi is 1 revolution. Cancel out my revolutions. Okay. So then I'm left with 7,200 pi, and that would be radians per minute. It's pretty darn simple. RPM stands for revolutions per minute. Okay. You guys all right with how I did that? You can just leave it like that if you want to. I'm fine with that. That'd be what, close to 22,000 radians per minute? I don't know. Punch it in the calculator real quick. What's 7,200 pi? I think it's like 22,000 something. We're pretty darn close to it. 22,619. So we can put that. 22,619 MB radians per minute. Okay? I'd probably just leave it as this because then we're going to use that angular speed for our linear speed. Okay?
No, why'd we cancel the 2 pi radian?
We didn't. We just multiplied. 3,600 times 2 pi.
Because
7,200 pi. We wanted to change it from the units it was in to our radian units. Okay? All right, so we had to do that then to get to this next point. Okay, so this next one, linear speed in terms of angular speed. So linear speed v of a point, a distance r from the center of rotation is given by v equals rw, where w is the angular speed in radians per unit of time. Okay, so v is that linear speed. So, again, linear speed on a circle would be, easiest way to think about it is if you have your tire. If you would mark one spot on your tire, okay, as you're going down the road, your tire is going to be rotating at a certain speed, right? If you would take that one spot on the tire, if you could essentially flatten it out, that's how fast you're moving. And essentially, that's what miles per hour is on your car. Okay? Your computer, the radius of your tire, those all those types of things weigh into that decision when it goes into your car's computer, then it reads out on your dash. Okay? Obviously, on other situations, we're not going to have that dial. Okay, situation like this. So you got a wind turbine rotating at a speed of 4 revolutions per second, so it's moving pretty quick. Blades of the turbine are 10 feet long. What's the linear speed of the tip of the blade? All right, so we're going to see if there's blades or a tire going down the road, how fast would it be going? All right, so let's look at this guy. I think this one's cool. So, first thing we want to do, if I can scroll a little bit. All right, how many revolutions are we making? And how long is it taking us to do that? 1 second. Okay, so we just found our angular speed before, right? Let's do that again. So my angular speed is W. Okay, so I have 4 revolutions in 1 second. So it's cruising. So let's change this guy to radians. So therefore, 2 pi radians over 1 revolution. Same as we did before. So therefore, I'm looking at 8 pi radians per second. Okay, this here is my angular speed. So that is how fast, okay, it's rotating. This is how fast this angle is changing. Okay, it is changing at a rate of 8 pi radians per second. All right, so now we find our angular speed. Now we can use that to find our linear speed of a certain point. So that's going to be our v here. All right, we have our radius. Well, my radius is 10 feet. That's given to us. So I have 10 times my angular speed that we just found, which is 8 pi. And that's 8 pi per second. Multiply that, we're looking at 80 pi radians per second. And you punch that puppy in a calculator, the thing's going 251 feet per second. So that means every point that is going around here is moving at a speed. And that's the point on the end of the blades. Okay, the point at the end of the blades is rotating around in a circle at 251 feet per second. So that puppy's cruising.
So would the points on the inside be moving faster?
They would actually be moving slower. The most extreme point on the outside would be moving the fastest because it's got to cover the most distance. As you get closer to the middle, it's going to move slower. Yep. So if you think about it on your car, your rim technically turns slower than your tire in linear speed. You know what I'm saying? Any questions on that, guys? All right, so that is the end of 1-1. So let me look at your homework here.